Okay, so hello and welcome back. So now that we got through an experiment in the previous video and some calculations related to that, we can actually do a couple more similar examples and then get to the next things. Okay, and I'm trying to use as much paper as I can. So now the next, I have another problem over here, and one more thing that I need to add to the previous circuit that we had. We had a circuit with, as you remember, we had a resistor and another resistor and a capacitor and so on. It was a kind of like a low pass filter, and we did a couple of calculations, and as you saw, the output that I got in the calculation was a little bit 1 volt different from the actual output that we got in the actual circuit. And the reason why that happens is that in such circuits that we actually had over there, the circuit was actually something like this. So it was a resistor over here, a resistor over here, and it was a capacitor. Okay, so this was the input voltage, and this was the output voltage. So this was, for example, R1, R2, and C1. So, and we were monitoring the voltage across these 2 points. Basically, these two were connected in parallel, and then both connected in series with this R1 over with this resistor over here. And the voltage that we got in the calculation was a little bit different from what we actually got in the experiment. And the reason why that happened, what I think is that basically what I know is that calculating the exact basically calculating how this resistor and capacitor in parallel are actually behaving in this circuit, it's a little bit complicated, and it's beyond the scope of what at least what we're doing right now. So we are a little bit, this is a little bit of simplification that we are doing, that we are saying that if, for example, you have a DC signal coming in, then you can imagine that this capacitor is not in the circuit, and then you have two simple, for example, resistors over here, and two simple resistors over here, and then that becomes just like a simple voltage divider circuit for a DC circuit. And then we also said that if AC is coming in, then you can simply imagine that this resistor over here is not there, and then you're dealing with a simple low pass filter, the way that we thought about the low pass filters that we had before. So of course we are kind of simplifying or oversimplifying things, and so therefore of course we're not going to get the exact output value of the voltage in the calculation. And when you if and when you want to do this kind of oversimplification or simplification or whatever you want to call it, you need to make sure that the reactance of this capacitor in this circuit is around 1/10 or less than the ohmic resistance value of this resistor over here. And in the circuit that we had before, that was not the case, meaning that I had this capacitor there, which was, I don't know, 0.01 microfarad. That was the value of my capacitor, and then this resistor over here, R2, was 1 kilo ohm. Okay, and then this resistor over here, R1, was also 1 kilo ohm, and the frequency I was basically working at, or the frequency that I mean, you have to basically hold on to one certain frequency, otherwise you cannot do any sort of calculation. So the frequency was 30 kilohertz. Okay, so now if you calculate the reactance of this capacitor at this frequency for this circuit, what you will get is that your reactance or X of C is equal to 1 over 2 pi times the frequency, which is 30 kilohertz, 30 times 10 raised to the power 3 hertz, times the value of the capacitor, which is 0.01 microfarad into 10 raised to the power negative 6 farad. And if you do this calculation, what you will get is 2 pi, not 2 times 10, 2 pi times 30 into 10 raised to the power 3 into 0.01 into 10 raised to the power negative 6, and then if you take the reciprocal of that, you will get 530 ohm. You will get 530 ohm, 530.5 ohm. Okay, and the resistance and the resistance of this resistor over here was 1 kilo ohm. So you see that the resistance, that the reactance of this capacitor is actually more than 1/2 of the resistance of this resistor R2. So of course, in this kind of circuit, you're not supposed to do this kind of thing. You're not supposed to, I mean, you cannot use this kind of oversimplification, because the reactance of this capacitor is actually over half of the resistance of this resistor. If the reactance is about 1/10 of the resistance of this resistor, then you can just simply ignore this resistor for an incoming AC signal. That's okay, and in that case, then your calculation is going to be also very close to the actual value that you would get in an actual experiment. So for example, if you go for a capacitor with some value like 25, for example, microfarad, if I swap this capacitor with a capacitor that is 25 microfarad, and then if I keep this resistor as 1 kilo ohm as it is, then what happens is that my X of C is going to be 1 over 2 pi times F, which is 30 kilohertz. Of course, the frequency is also important. The frequency is going to also decide what sort of reactance I'm going to get here. So the frequency over here is way too high, for example, for this kind of oversimplification. So, and I'm going to show you what I mean by that. So 30 kilohertz would be 30 times 10 raised to the power 3 hertz, and the value of my capacitor is actually 25 microfarad. 25 microfarad into 10 raised to the power negative 6 farad. So now if I do this calculation, what you will see is that basically if you calculate 2 pi times 30 into 10 raised to the power 3 into 25 into 10 raised to the power negative 6, I made a mistake, 2 pi into 30 into 10 raised to the power 3 into 25 into 10 raised to power negative 6 is equal to 3/2 pi. Take the reciprocal of that is equal to 0.20. So it's equal to 0.20, which is okay. I mean, this kind of thing, I mean, at this reactance, this is about I don't know, 1/10. It's way less than 1/10 of it's way less than 1/10 of 1 kilo. So if you, for example, if you compare 1000 ohm to 0.20, what you will get is times 10 would be 10,000, times 10 would be 2, and then 5 times 2 is equal to 10. So that's 5,000 times smaller. The ratio is 5,000. So that's actually not 10 times, but 5,000 times smaller than the resistance of this resistor. Meaning that if I take this resistor, if I take the resistor, this resistor, which is 1000 ohm, and if I divide it by 5,000 times smaller, meaning that if I divide it by 0.2, I will get 5,000 over here, right? So that means that now if you, for example, if basically you did this calculation and you got some value, for example, like some value like 0.1 ohm or something. So 0.1 ohm, the ratio of 1000 ohm and 0.1 ohm is equal to, I'm sorry, not 0.1 ohm, or actually 100 ohm. 100 ohm, that would be basically 10 times. So all the way up to 100 ohm reactance, if, for example, if your resistor over here is 1 kilo ohm, then all the way up to 100 ohm reactance over here, if you had that, then you could simply oversimplify, and for a DC, for an AC signal, you could simply ignore this resistor, and then basically say that okay, so when AC comes in, it's going to just simply behave like a simple low pass filter, for example. Otherwise, when you have a 1 kilo ohm resistor over here, and when your reactance over here is 530 ohm, then of course this resistance over here is only about 2 times the reactance over here, and then of course you cannot ignore this resistor over here. You could, for example, increase the value of this resistor so that the ratio is something like 1 to 10, but then that will basically change other things in your circuit as well. Then that would basically change the way that the circuit would behave in the case of DC signals coming in. Okay, so all of these things are basically considerations things that you have to take into consideration before you use this kind of oversimplification. But if again, I repeat, if the reactance of this capacitor over here is 1/10 or less than the resistance of this resistor parallel with that, then of course you can use oversimplification, and then you can get away without going through the very complicated calculation that would be involved with finding the exact output voltage over here. Okay, so that is that. Now, for example, for let's have another circuit over here. Let's say that you have a another circuit over here. So let's say that you have a circuit. So you have a resistor over here. A resistor over here goes to ground. A capacitor over here that also goes to ground. And this is your V of out. And this over here is your V of in. And this is basically 1 kilo ohm. This is 1 kilo ohm. This is 25 microfarad. And you want to find the reactance of this capacitor in this circuit, and you want to find the DC output voltage. You want to find the AC output voltage, AC V out, and you also want to find the attenuation. And attenuation is basically how much your circuit is actually decreasing the incoming signal in case of DC and in case of AC. So for example, when you calculate the DC output of this voltage, then you have a certain amount of DC voltage coming in and a certain amount of DC voltage going out. And then if you take the ratio of those two, you will have the attenuation related to your DC signal. And then when you do the same calculation for your AC output, you have when you calculate that, you have certain amount of AC coming in, a certain amount of AC going out. Take the ratio of those two values, you will get the attenuation related to your AC attenuation, and that's usually basically expressed in terms of logarithm, and then they have given it also some unit as bell or decibel, which I think we will talk about somewhere over here. There is no talk about decibel or bell, but it's usually, that ratio is usually given as, used as the argument of a log function, and then it's usually in engineering it's basically customary that people talk about these ratio in terms of decibel and not just a simple ratio, so that they can work with those numbers more efficiently, and so that everybody understands what everybody else is talking about. Okay, so I take a few minutes rest and I'll come back. We will do this circuit together. Okay, so about this circuit that we have here is basically you have this 25 microfarad capacitor here, and I think I need to move this a little bit over here. So you have a 25 microfarad capacitor here, and these two 1K ohm resistors. So since we want to simplify this circuit anyway without exact calculation, first you need to check the reactance of this capacitor. If that's around 1/10 of this resistor or less, then you can actually do the simplification. Otherwise, the value that you calculated would actually be wrong, like what we did in the previous video, I suppose. So now what I want to do is that actually I want to find the x sub c of this capacitor, the reactance, which is 1 over 2 pi the frequency times the frequency, and the frequency over here is the frequency over here is, let me see. Okay, so in this circuit basically we have the V of in, the frequency is actually 600 hertz, and basically this capacitor is 25 microfarad. Keep these in mind, these two values, keep them in mind, because we have another a similar exercise like this, and then in that circuit we are going to change these two a little bit so that we can get slightly different attenuation from the circuit. Okay, so now if the frequency is 600 hertz, so that's 1 over 2 pi fc, which is equal to 1 over 2 pi, the frequency is 600 hertz, times the capacitance, which is 25 into 10 raised to the power negative 6 farads, and that's equal to 2 pi times 600 times 25 into 10 raised to the power negative 6, and the reciprocal of that is equal to 10.61, or 10.6 actually, is equal to 10.6 ohm. 10.6 ohm is actually around 1/10 of, very close to 1/10 of 1 kilo ohm, because this is 1000 ohm. 10 is am I right? So let me see, 1 kilo ohm over here, 1 kilo ohm over here, 1000 ohm, and that is basically 10 ohm. So that's basically 10 times, right? Okay, so that is 1/10 of, okay, right. Okay, so that is 1/10 of the, meaning that 10 is actually 1/10 of, let me check this calculation here. Well, actually this is basically 10 ohm is actually 1/100th of a, that's what confused me. Actually basically 10 ohm is actually very close to 1/100th of 1 kilo ohm. And if you can go down to at least 1/10, then of course you can go ahead and do the simplification, meaning that if the reactance here was even 100 ohm, then you could do it. So now the reactance is 10.6 ohm. So that what that means is that you can basically, the part for the DC output, if DC came into this circuit, you would have this, you could, I mean, since the reactance of this capacitor is actually 1/100th of the resistance of this resistor, you can actually imagine that if DC came in, that you could actually ignore this capacitor over here, and then you would have these two, basically these two resistors in series. So then you would have a circuit like this, and then this would be your V of in, and this would be your V of out, and I don't really know, let me see, Okay, so the DC offset over here is actually 10, is like the DC input voltage is 20 volts. So we have in 20 volts DC, and the AC input is 10 volts. 10 volts, basically peak to peak AC basically. So these are the voltage values of this circuit. So when DC comes in, you have 20 volts DC coming into this circuit. 20 volts DC, and then you can of course ignore the frequency and everything. So then you have a 1 kilo ohm resistor over here, 1 kilo ohm resistor over here, and the capacitor is not there. So then the voltage, you would have a simple voltage divider circuit. You would have half of your input at this point, because this is a voltage divider in which you have basically two resistors in series of the exact same value. So 1 kilo ohm, 1 kilo ohm, that here this point would give you exactly half of the input voltage, which is 10 volts. If you want to actually calculate that V of out over here, V of out, or if you call this for example R2, which is equal to V of R2, is equal to R2 over R1 plus R2 times V of in. Okay, so times V of in. So that's basically 1 kilo ohm. So 1 kilo ohm over basically R1 plus R2 is 2 kilo ohm times V of in, which is equal to 20 volts. And then these two will cancel out. We have 1/2 of 20 volts, which is equal to 10 volts. 10 volts DC. So that's your DC output. Now, if you were to calculate the AC output, then you could simply ignore again for the same reason that basically the reactance of your capacitor is 1/100th of this resistor over here. If AC came in, you could ignore this resistor, and then your circuit would be simply like a circuit like this. So you have a capacitor over here, 25 microfarad, and this would be your V of in. This would be your V of out. Your V of in would be 10 volts peak to peak. At the frequency is 600 hertz. Okay, and your V of out would actually be, this is a 1 kilo ohm resistor. Okay, so your V of out for this circuit would simply be, your V of out for this circuit would simply be the I mean, what you're doing here, you're actually monitoring the voltage across this capacitor, and so then you have to take the ratio of the reactance of this capacitor by the total resistance in this circuit. So the reactance of this capacitor is X of C at the frequency that we calculated, and then you divide that by the total resistance in this circuit, which is, in this case, is actually called impedance, times V of in. Now, we have already calculated X of C, but Z we have to calculate it. So your Z, as you remember, is the square root of X of C squared plus R squared. And that's equal to 10.6 squared plus R squared, which is 1000 squared. Calculate that. So 10.6 squared plus 1000 squared, that's equal to 1000.06 actually. Equal to 1000.06 ohm. 1000.06 ohms. So then your V of out is going to be equal to X of C, which is 10.6 ohm divided by 1000.06 times V of in, which is basically 10 volts peak to peak, times 10 volts peak to peak, and that's equal to actually 10 times 10.6 is 106 divided by 1000.06, and that's equal to 0.105, so 106, 0.106 volts peak to peak. That's 106 millivolts peak to peak. Okay, so that is that. Now the attenuation, the DC and AC attenuation for this circuit, the attenuation when you want to calculate that, so here your V of out was your V of out would be 0.106 volts peak to peak, and here was 10 volts peak to peak. Now about the attenuation, okay, about the attenuation, so when we were talking about the DC input, your DC input was 20 volts DC. Your DC output was 10 volts DC. So your attenuation, I suppose, is, I think it's input to output. Or I think it's input to output. Of course, you can then, if what I'm saying is wrong, you can change the ratio, meaning that output to input. You can do whatever you want depending on the situation. You can change the ratio. The numerator and denominator of the ratio doesn't matter. It's just that you need to understand what you have done with the ratio. That's all. That's basically all. So your attenuation would be, or I'm not going to call it attenuation. I'm just going to call it the ratio of the input to output. So your input to output would be equal to 20 to 10, which is equal to 2. Meaning that your output voltage is actually, meaning that your output voltage is actually half times the, meaning that the output voltage is half of the input voltage, or your input voltage is twice the output voltage. That's basically what that means. So, and then about the AC part, so your input was 10 volts peak to peak, 10 volts peak to peak. Your output was 0.106 volts peak to peak. So then your input to output would be, your input to output would be 10 divided by 0.106, which is equal to 0.106 is equal to 94.34. 94.34. So this ratio, you see, your input is actually about 100 times your output when it comes to AC, but when it comes to DC, your input is only 2 times your output. So that's basically the difference between AC and DC basically in this circuit. Okay, now we can do, basically we can make some changes to the same circuit, meaning that for this example we had this circuit over here, And what I want to do now, I want to basically I want to change this capacitor to a capacitor 10 times the value of this capacitor, meaning 250 microfarad instead of 25 microfarad. But I want to reduce the frequency to 1/10 of the frequency that we had before, meaning that over here we had 600 hertz. I want to reduce the frequency to 1/10 of that, 60 hertz, see what happens to input output. Okay, but that I will do in just a few moments. I don't want to wear myself down. Okay, so the next thing that we have here is well, the same circuit actually, the same circuit but with a few changes. So the changes that I want to make is that basically I have the same circuit here, so a resistor over here and a resistor over here, and that goes to ground, and then a capacitor over here, and that goes to ground too. And here I have my V of out, and here I have my V of in. So it was basically 20 volts DC, 10 volts peak to peak. Now what I want to do here is that I want to change the frequency to 60 hertz instead of 600 hertz that we had. So I want to change the frequency to 60 hertz, and the capacitor that I had was actually 25 microfarad. So now I want to change the capacitor to 250 microfarad, but the two resistors are going to stay the same, 1 kilo ohm and 1 kilo ohm. Now I want to calculate the same things for this circuit and see how the input-output ratios are going to change. Okay, so now in order to do that, so first you need to we need to find the reactance of this capacitor at this frequency, see what that is, and then if the reactance is at most at least 1/10 of a I mean the highest value that it can take is 1/10 of this resistance over here. So it should be it should be at least 1/10 of this resistance over here, meaning that I repeat this, the reactance over here should be at most 1/10 of the resistance over here, and then you are allowed to kind of oversimplify things in order to do your calculation the way that we are doing it right now. So then my x of c is actually equal to 1 over 2 pi fc, which it's actually 1. So it's equal to 1 over 2 pi, the frequency is 60 hertz, times the capacitance is 250 microfarad into 10 raised to the power negative 6 farads. And you see that I have basically changed the the frequency was actually 600 hertz. I have reduced that to 1/10 of the original value, and now it's become 60 hertz. The capacitance here was basically 25 microfarads. I have increased that to 10 times the original value. So then of course the reactance is not going to change, because you have decreased this value by 1/10 and you have increased this value by a factor of 10. So the reactance is not going to change at all. So what that means that this value is equal to 2 pi times 60 times 250 into 10 raised to the power negative 6, and if I take the reciprocal of that, it's going to be 10.61. It's actually going to 10.61 or 10.6 basically ohm. And as you can see over here in the previous case, the reactance was again the same value, 10.6 ohm. So you can actually play with the value of your capacitor and play with the value of your input frequency, and basically do it in such a way that there is a balance between them, so that you don't play much with the value of reactance of your capacity, so that then your reactance doesn't change much in the reactance of the capacitor doesn't change much in the circuit. Okay, and then of course, depending on that, you can do different things in your circuit, but that's something that you can see over here. Now the next thing that I want to calculate is the voltage, the output voltage when there is when I'm inputting a DC signal into this circuit. So DC voltage. So when you're inputting a DC signal into this circuit, you can think of the circuit as a circuit having only these two resistors. So then you have basically the resistor over here, and that's all that you have. That's V of in, that's V of out, that's a 1 kilo ohm resistor, that's a 1 kilo ohm resistor, and then your input voltage is 20 volts DC, and that's all. So then again, your input, your V of out, is going to be basically, if I call this R2, and if I call this R1, it's going to be R2 over R1 plus R2 times V of in, which is equal to 1 kilo ohm over 2 kilo ohm times 20 volts. Now this is going to be equal to 1/2 of 20 volts, which is equal to 10 volts DC. So that's basically, so you see that that by changing the frequency and the value of this capacitor over here, the way that we did it, actually the DC output actually did not change in the circuit. Now let's see what happens to the let's see what happens to the the AC output. So when I inject AC into this circuit, the circuit is going to look like something like this. This is V of in, this is V of out, this is a capacitor 250 microfarad, and this is a 1 kilo ohm resistor, and the frequency is actually 60 hertz, and the voltage is 10 volts peak to peak. Okay, so then what happens here is that your V of out here is going to be the reactance of this capacitor dividing by the impedance of the circuit times V of in. The reactance we have already calculated, so your impedance is equal to the square root of x of c squared plus r squared. That's going to remain the same. That's going to remain the same. So that's going to be equal to 10.6 squared plus 1,000 squared, which is equal to 1,000.06 0.06 0.06 ohm basically. And then your V of out is going to be X of C divided by Z times V of in, which is equal to 10.6 if I'm not wrong. What was the reactance? What was the reactance? 10.6 divided by 1000.06 times 10 volts peak to peak, which is equal to 106 divided by 1000.06, and that's equal to the same output. 106 divided by 1000.06 is equal to 0.106 volts peak to peak. So now the ratios that you have, the DC to the input to output ratios, when it comes to DC, your input to output is 20 to 10, which is equal to 2, the same ratio. And when it comes to AC, your input to output is equal to 10 volts peak to peak to 0.106 volts peak to peak, which is equal to the same value really, 94.34. So you see that by changing the value of this capacitor and simultaneously changing the frequency, your your filter is going the behavior of your filter is going to remain the same. Okay. So now let me take a look at these examples. Let's see what is left here, and then I'll be right back with you. Okay, so far we have actually covered everything. So the next thing that we are going to talk about is going to be inductors in AC circuits, and I'll see you in the next video. Thank you.